So I'm going to talk about work that we've been doing on the automatic statistician. This is really part of a larger research program that I have. A few years ago, I was asked to give a talk where they said I have one slide to describe my research interests, so it forced me to produce this slide. The interests haven't changed since a few years ago. What it forced me to realize was that the thing that really drives me is the idea that we could further automate machine learning. Machine learning practice, ironically, is very labor intensive. So, even though machine learning is all about getting computers to learn from data, the way it's actually done is that people spend a lot of time applying their sort of expertise and applying their little tricks to getting learning algorithms to do something interesting with the data that they have. And I think we should just go one step further and look at that process and try to make that more intelligent, more rational, and more efficient. And so many of the things that I've been doing relate to this theme of automating machine learning. The talk today is firmly focused on this bit, the automatic statistician, I'm also incredibly passionate about a few other areas, probabilistic programming, which seeks to automate inference in probabilistic models, methods for more automatically scaling up to very large data sets, methods for allocating computational resources in a rational way. Machine learning is an actually very resource-hungry practice, and we are being incredibly inefficient with the way we use computers. And so applying levels of rationality to that, I think, is really important. I'm very passionate about Bayesian optimization. This is something that we actually use quite a bit within Uber, for example. Tools for optimizing expensive functions. Bayesian deep learning, again, sort of deep learning has taken off as a hugely impactful area of machine learning, but there's some limitations to current deep learning practice, and I think probabilistic approaches help with that. And Bayesian nonparametrics, which is another area that's always been in the background as a fundamental tool that is at least important to know about, if not to use on an everyday basis. So these are my interests. Currently, I'm not going to talk much about what I do at Uber. It's not because it's secret, actually. I'd be happy to talk about it. In fact, I've given a talk about that. I'm happy to answer questions about that at the end if people are interested. What I'm going to focus on is this problem of automating machine learning. And this is something that obviously many, many people have thought about over many years. This is a figure that's, you can't really see it well, but it's a figure that relates to the data analysis process. And essentially, the takeaway message is that in the data analysis process, there are many, many stages, many of which are incredibly important, but often quite neglected and not really very, let's say, exciting in terms of like writing research papers and so on. But these are the stages of processing that are absolutely critical in terms of getting value out of your data. So things like automating feature selection, transformation understanding. I put the word automating in front of all of them. Most of these things are done manually these days. But the process of dealing with the raw data and turning it into a usable form, the actual data collection process and experiment design, where did the data come from? How do we collect more data? The thing that I'm going to focus on quite a bit during this talk is model discovery and explanation, which is once you have the data, what model, it's a matchmaking process, what model do you use to answer the questions you're interested in from that data? And then the explanation bit is interesting as well. Once you've done that, how do you explain what you've done to other people? And then automating allocation of computational resources. I'll touch upon this a little bit. Automating inference. By that, I mean things like software frameworks like probabilistic programming languages that allow you to sort of sidestep the whole deriving things in hand, implementing the inference algorithms. I would put automatic differentiation tools also within this bucket. So basically, these are tools that have really revolutionized the practice of machine learning because people don't have to do derivatives by hand, code them up, and then debug them. Okay. So there are many stages of interest, and I think we need to handle all of these to really get to the next stage of extracting a huge amount of value from the data. So the thing I'm going to really focus on is automating model discovery, which is this automatic statistician project. The sort of subtitle for this is an AI for data science. I'm not really interested in general AI. I think general AI is a bit bogus. You know, actually, I think if you pick a limited domain like data science, we can do interesting things that we would call intelligent data science. And the nice thing about this project is it has a tremendous amount of overlap with, for example, the priorities of the Alan Turing Institute. So the Alan Turing Institute is the National Institute for Data Science and Artificial Intelligence. So you know, it's fun to be working on something like that because it brings these two fields together. And in fact, the work that I'm going to present here has a closely related sister project within the Alan Turing Institute, which is called AI for Data Analysis, which is really focusing on some of the earlier stages of this data analytics pipeline, whereas I'm going to talk about more the model discovery and explanation side of things. Okay, so just a pointer to that really exciting project at the Turing Institute as well. Okay, so what's the problem that the automatic statistician is trying to solve? So the problem at a very basic level is that we've got lots of data. There's a lot of value in that data. And we'd really love to be able to extract that value. But we can't afford, even if we're a hedge fund, we can't afford to hire enough data scientists to get all that value out. Okay? And actually, there are not enough data scientists, machine learning researchers, and so on out there to meet the demand that all of the data is presenting. So there are two approaches to that. One of them is, you know, what professors do is you train up more people to be data scientists so that then they can get hired by industry or other sectors. And the other approach is you sort of automate what they do. And, you know, the negative way of thinking about that is, you know, you're putting people out of a job. The positive way of thinking about that is you're giving them superpowers so they're incredibly more efficient than they were before. Okay, and that's the way I like to think about it. When I spoke to a bunch of statisticians, I think one of the things I might have done there cheekily was change the title to be the automatic data scientist, and they weren't offended about automating data science as much as they would be offended about automating statistics. So statistics is such a deep and important field, and surely it can't be automated. But data science, I'm sure that could be automated, right? I haven't really given the talk about automating AI researchers to an AI audience. I think that would be fun as well. Okay, so that's the problem we're trying to solve at a very high level, and the solution, if you can do the error correcting decoding here, is to develop a system that automates model discovery from data. So the real ambition is actually what I would love to have is a system that does everything end to end. And basically, what you do is you have a conversation, you meaning the human, has a conversation with the system about the data, where the system can ask you questions about the data, and you can ask the system questions about the data. And through that conversation, you figure out what's going on that's of interest. And you might also do, you know, high throughput predictions of stuff if you want on the side, but a lot of this centers around, you know, really trying to understand what's in the data. Okay? And one of the key ingredients in this is that matchmaking process, discovering a good model for the data. And I think that's really done in a very ad hoc way. And it's actually quite a creative process, right? You know, most of the time people get a data analysis problem. They'll think of the few models that they learned about when they were, you know, in PhD students or master's students or whatever. And those are the models that they'll apply to the data analysis problem that they have, because those are the models they're comfortable with. But the space of possible models is absolutely huge. And if we were just a bit more systematic about searching that space, we might find much better models to account for the patterns in the data. But of course, with that comes some risks. So here are the ingredients of the automatic statistician. The way you sort of picture this is a system where data goes in at one end and a bunch of things come in at the other end, including a report that describes to you what's in the data. And it could be an interactive report or it could be a static report. I might show you a video, if we have time, of this thing in action. And when I talk about data, of course, data could mean almost anything. To keep my life simple, I'm talking about, think of tables of numbers. Okay, it's something like you might find in a spreadsheet. They might not be purely numerical. We should be able to allow for other kinds of data types. But a table with rows and columns, okay, nothing really much fancier than that. And so what do we want in between the raw data and the report and other things at the other end? Well, what we want is to replicate some of that creative process of coming up with a good model for the data. And to do that, what we need is not just to test out 2 or 3 models or a handful of models. Ideally, what we'd like to have is an open-ended language of models, a way of expressing many different models by combinations of some simple primitive operations. And I'll describe a very, I think everything that we're doing is sort of early days in this effort, but I'll describe a system that kind of does that in the context of time series models. Now, of course, the downside of having this open-ended language of models is that the number of models that you might consider for your data set is absolutely huge, right? And so that has 2 downsides. One of them is then you have to search that space for a good model. So you want an efficient search procedure for finding good models. But also, you have the risk of overfitting. You want a method that is principled for evaluating the models and the data. So a method that really trades off the complexity of the models with the fit to the data. Okay? Because if you don't do that, you'll always be able to find some model in this vast space with enough time that captures all sorts of spurious patterns in the data, and that's just classic overfitting in model space. And then the last thing that we want to do is we don't want to be black boxes. So one of the big criticisms about machine learning these days is, and especially deep learning methods, which I love and are wonderful in many other ways, but they're actually terrible black boxes in the sense that they have millions of parameters, inputs go in, outputs come out, and it's hard to know what happens in the middle. It's hard to give any sort of explanation for the decisions that come out of these systems, and it's hard to rely on them to robustly generalize to new situations. So the explainability and transparency is something that we care about because that's something that actually a lot of people find useful. It depends on the application domain, but I think even in finance, if you have a model that seems to perform very well, but you can't really explain at all what it does, people might not trust allocating lots of money to it. So it depends on the flavor of where you work, but that, certainly I've experienced that. Okay, so now I'm going to go a little bit into the details. And so what we're going to look at is not the space of all models. Obviously, that's too big. But let's limit ourselves a little bit to, for now, regression models. At the end of the talk, I'll talk about some generalizations to other things. So regression consists of learning a function, call it f, from some inputs to some outputs y, where the outputs are generally thought to be continuous values. And the data is just input-output pairs. So a very classical, simple machine learning problem. Of course, also a problem that underlies over a century of statistics. And so what we want is a language of regression models that captures some of the simple interpretable things that statisticians have been doing for over 100 years. Like, for example, fitting linear models. We want to be able to fit linear models and explain them. We want to be able to fit polynomials or exponentials or other kinds of curves. But we don't want to limit ourselves to these types of models. We want to be able to describe the functional relationship between x and y in simple intuitive forms, like maybe it's a smooth function, or it's a periodic function, or it's a monotonically increasing function, etc. So terms like that that people might find useful. And then what we would like is for inference to be tractable for all the models in the language. It doesn't have to be. If it's not tractable, if it's computationally expensive, we can always approximate it. But there are a class of nice models that have some of these properties. So the models that we're going to use for this part of the work, and one of the workhorses, but not the only workhorse of the automatic statistician, is Gaussian processes. So raise your hand if you know about Gaussian processes. Raise your hand if you don't know about Gaussian processes. It's about capturing the shy people who don't raise their hands with either question. Raise your hand if you've used Gaussian processes. OK, good. So Gaussian process is just a way of defining distributions over functions. OK, so what we're trying to do is learn a function. What we're going to do is start out with a distribution over functions, and then condition on the data to get a posterior distribution over functions. So basically, Bayesian inference is one of the other workhorses that we use. So the Gaussian process is a distribution over functions such that any finite subset of function evaluations, so f evaluated at x1, x2 through xn, that n-dimensional vector has a multivariate Gaussian distribution. So if that's true for any set of n x's and all those multivariate Gaussians are coherent, then there is an object called f, which is a draw from a Gaussian process, basically. Now, just like a Gaussian is defined in terms of a mean and a covariance, or a variance. A multivariate Gaussian is defined in terms of a mean vector and a covariance matrix. A Gaussian process is defined in terms of a mean function, mu of x, and a covariance or kernel function, call it k of x, x prime. So we're trying to express beliefs about functions from x to y. And the mean tells us, on average, where we think the function is going to be. And what the covariance tells us, k of x, x prime, is basically how similar or correlated is the function value at x with the function value at x prime. So typically, covariance functions where the covariance drops with the distance between x and x prime give us smooth functions. But there are other kinds of covariance functions out there. So for example, periodic functions will have x being highly correlated with, f of x being highly correlated with f at x prime if it's one period away, okay, like a week away or a day away or whatever the periodicity is. Okay? And the covariance function that's used in a Gaussian process is something that is identical to the kernel that's used in kernel machines, which were very popular in the 90s and were the most exciting thing in machine learning in the mid to late 90s. Here's a Gaussian process in action. Essentially, the process that you're seeing with these 4 panels is what I call learning. Okay? So what's going on is before I observe the data, ignore all the pixelation, of course. Before I observe all the data, I have a prior over function values that's very broad. I don't know what the function is going to be. Okay, so that's this whole shaded area. Now I observe a single data point. Imagine I observe this single pair of x and y. Well, what's going to happen then is that I've learned something about the function at this point, that under this kernel, it tells me something about the function nearby, but again, far away, I don't know anything about the function. Now, if I have 2 data points or 3 data points, I start to learn more and more about the function. So this envelope of uncertainty shrinks as we go to more data and as we go closer to the training data. So this is learning when we're assuming that the function values are noise-free, but you can super trivially generalize this to learning when you assume that you observe noisy values of the function. It's a simple, beautiful illustration of Bayes' rule in action. All that's going on here is successive applications of Bayes' rule, where I start from the prior, I observe 1 data point, I get a posterior over functions, which is now the prior that I observe another data point with, et cetera. Okay. Now, Gaussian processes are interesting because you can actually relate them to a lot of other models. So one relationship I think I'm not talking about at all is that they're related to neural networks. So in fact, maybe I get that relationship out of the way. Radford-Neal in 1992 roughly proved that if you had a neural network, a multi-layer perceptron, with infinitely many, one layer of infinitely many hidden units, then under some fairly weak conditions on the prior over the weights, that converged to a Gaussian process. So what happened in the community back then was neural networks were a complete headache for people. People hated them because optimization was hard, and they had local optima, and so on and so forth. And when Radford-Neal proved this, people said, oh, great, we can throw away neural networks, and we can just use Gaussian processes, where everything can be done analytically using a couple of lines of linear algebra. So it was revolutionary. It was wonderful. But as David Mackay said many years later, maybe we threw away the baby with the bathwater. Maybe neural networks were worth looking at. And then this came back with a vengeance in around 2012 with the deep learning revolution. Now, interestingly, we have a paper just out a few weeks ago where we extend Radford-Neal's result to not just infinitely wide networks that are shallow, but also deep and wide networks. So depth doesn't buy you anything, actually. If your network is really wide, then you're still going to end up in some limit basically with a Gaussian process. So it's interesting just to think about that. Here's another way of deriving Gaussian processes. So you start with linear regression, sort of the most basic model in all of statistics. And then you do a few operations to linear regression. So one operation I can do to linear regression is I can, instead of the output y being a real valued variable, when I'm trying to do regression, I think of a discrete or categorical variable, like, for example, if I'm trying to do classification. So these magenta arrows are turning regression problems into classification problems. So an example of a linear model that does classification is logistic regression. There are other examples here as well. So I think of that as the classification version of linear regression. Another operation I can do to linear regression is, instead of finding a point estimate of the parameters, instead of solving for the parameters using least squares or something like that, I do Bayesian inference over the parameters. So I come up with a prior on the parameters, and then I multiply by the likelihood, and I get the posterior. So that would be Bayesian linear regression, a textbook model if you're doing Bayesian statistics. Those are the blue arrows, the Bayesian versions of point estimate or maximum likelihood models. And then the orange arrows are applications of the kernel trick. So the kernel trick, again, wildly popular in the mid-90s and so on, is the idea of doing transformation from your raw inputs, x, to some high-dimensional feature space, call it phi of x, and then doing a linear model in that high-dimensional feature space. So your model is nonlinear in x because you mapped it into this high-dimensional thing. but it's still linear in the parameters, so all the computations are super easy. So kernel regression is application of that trick. And if you think of the kernelized version of a linear classification model, you get something like kernel classification, which is where support vector machines live, among other models. And Gaussian processes live at this corner of this cube. They're a Bayesian version of kernel regression or a kernelized version of Bayesian linear regression. And if you apply all three of these operations, what you get is Gaussian process classification, which is like the Bayesian sister of support vector machines. So I've given a talk which was titled Why I Never Use SVMs. And the reason was not because I don't like SVMs, but because as a Bayesian, I can always use Gaussian process classification instead, and I'm much more comfortable doing that. Okay. So these are closely related. Anyway, so that's a little deep dive into sort of the relationship of Gaussian processes with other things. But what can we do with the kernels in a Gaussian process? So here are some things that we can do. Well, I talk about language of models. So what do I mean by language of models? Well, language has this property where you can take words and compose them together to get complicated, interesting sentences. So we want that in the space of models as well. So the words or atoms of our language are going to be a few simple base kernels. So like the squared exponential, periodic, linear, constant, and white noise kernels are a few of the basic kernels we can use. And what these kernels correspond to is basic properties of functions we might be interested in. Like squared exponential corresponds to smooth functions. Periodic corresponds to periodic functions. So here we have just two samples from functions with that kernel. Linear corresponds to linear functions, and constant corresponds to different constant functions. The white noise kernel corresponds to functions that are just white noise. Okay? These are the basic functions. Now, from these basic functions, we can compose them with a few operations to get other valid kernels. And the two main operations, actually there are three operations. The third one we use for time series, and I'll mention that in a minute. But the two main ones are addition and multiplication. So adding or multiplying kernels gives me another kernel. So for example, linear multiplied by a linear kernel gives me a distribution over quadratic functions. And by closure, I can get all polynomials with that. Squared exponential times periodic gives me locally periodic functions. Linear plus periodic gives me periodic plus some trend. So functions that look like this. They have some linear trend and some periodicity on top of that, etc. Sorry, the other operation that we use, which is I think also interesting from a finance perspective, is the change point operation. So basically, if I have a valid kernel, I can compose it with another valid kernel with an assumption that the function somehow changed from being drawn from this kernel before some point in time, think about time series, and then from this kernel after that point in time. So that change point operation gives me still a valid Gaussian process, and we use that because in a lot of the time series that we model, that's what we're actually really interested in. We're interested in where did the behavior of the time series change. Okay, so now with those ingredients, let's put them together and look at the search space and the evaluation of models. So in terms of search, here's what we do. And I always like this, even just for, for practical purposes when, you do data analysis. You want to start from simple models and move towards more complicated models. And that's exactly what we implement in our automatic statistician. So here is a time series. This is the MAUNA LOA KEELING curve time series. And this curve is carbon dioxide concentration on top of Mauna Loa, which is a volcano in Hawaii. And this is a famous data set because it's been used in climate science to talk about like global warming and things like that. But for us, it's just a bunch of data points along time. Here, this axis is years. And here what we're doing is we start with a really simple Gaussian process, like, for example, the constant function or something like that. And then we apply different operations to search over different kernels. And here is the first thing that I found. So in this particular language of kernels, we're looking at something called rational quadratic kernels as well. But we got rid of that after a while because those models are not that useful. But anyway, so it finds a kernel. And what you can see from that is that that models the data very well. And after the dashed line is extrapolation. When it does extrapolation, the extrapolations look a bit funny to us, right? I mean, there is no science to extrapolation. They could be right. That could be what's happening. But it seems counterintuitive. There seems to be a pattern here, and those extrapolations don't look great. And you can also see the uncertainty that it has in extrapolation, which I think is kind of useful to look at. So then it expands on the current best kernel by applying these operations, multiplication, addition, and change points, to find another kernel that explains the data a bit better. So this is periodic plus rational quadratic. And then another kernel, which is squared exponential times periodic plus rational quadratic, that explains the data better, and so on. And then it stops at some point, which is squared exponential plus squared exponential times periodic plus rational quadratic. That's just shorthand for the kernel that is found for modeling this data. And where does it stop? Well, it stops using a criterion called the marginal likelihood. And the marginal likelihood is integrating over all the parameters in your model the probability of the data under that model. And the nice thing about this, this quantity, which is also sometimes called the integrated likelihood or the evidence, and sometimes it's referred to as like the Bayes factor or Occam's factor, this quantity really elegantly trades off the amount of data that you have with the complexity of the model that you're trying to fit. So it automatically trades off things so that you don't get either underfitting or overfitting given your assumptions. So basically, in a subjective Bayesian framework, you have to make some assumptions that you start out with, some priors and so on. Then under those assumptions, this will naturally trade off, so you don't have to do cross-validation or anything like that. Okay. So it uses the marginal likelihood, and it stops at some point, and then it says, that's the model that I most believe in from the models that I've explored in my search. And what you can see is that model actually has, you couldn't really see much difference on the training data, but the extrapolations of that model are much more sensible. And in fact, often this procedure gives you very intuitive extrapolations, the kinds of things that a human would draw. In fact, I saw just this past year, somebody wrote a research paper where they got humans to do extrapolations of time series. And then they compared them to the outputs of the automatic statistician versus some other time series models. And they found that human behavior was more similar to what the automatic statistician did than a lot of these other time series models. So this was not in my group. I mean, I could find the paper. I thought it was quite amusing to actually do that experiment. But it's intuitive. And when it's not intuitive, it's one of two things that have happened. One of two things go wrong. One of them is that your priors were really weird and you didn't realize it. Your priors didn't actually capture your own intuitions. That's one failure mode. And the other failure mode is that your search procedure just got stuck in the wrong place, or the approximation to the integrals that you had to do was poor in that case. So something went wrong, and you can kind of diagnose what went wrong. OK, so this is what happens. Here's another data set. This is, again, it's actually quite hard to see. Cryptographically obscured for you. So this is a data set of airline passengers, monthly airline passengers from the late 40s to the early 60s. And you can see it when you do connect the dots a little better. So this is the raw data. After the dashed line is extrapolation. When you connect the dots, what you see is a periodicity, but it's not a strict periodicity. It's kind of an approximate periodicity, and the amplitude gets bigger over time. And then the extrapolation for the next year or two looks really sensible, I would say, from the model. So the text here is actually the model's own explanation in words for what is discovered. So this is computer-generated text. What it says is, for this data set, 4 additive components have been identified in the data. And then it orders them by amount of signal that were explained by each of those components. So a linearly increasing function, well, you can sort of see that. An approximately periodic function with a period of 1.0 years and with linearly increasing amplitude. So the only thing it knows is that the unit is years here. And so it produces that. It's not exactly periodic. It's approximately periodic, which also makes sense. And you can see that it's got linearly increasing amplitude. I could actually write down for you what the kernel expression is that translates into this phrase in English, basically. And then the third and fourth components, you can't actually see so easily by eye. It says that there's also a smooth function underlying it and an uncorrelated noise with linearly increasing standard deviation. You can't really see that by eye, but actually, the report, this is like the few lines of the executive summary of the report. The full report, which is 10 to 15 pages long, has sections where it removes the first 2 components of the signal, and then it shows you in the residuals that there is some smooth function, and then it says, and this is why I think there's a smooth function. It removes that, and it shows that the noise increases linearly in amplitude, et cetera. So the report tries to explain why it's come up with this summary. Okay, so these are the first pages of a couple of these reports. Maybe I could show you one of these reports. Let's see if that works. Okay, so here's another data set. This is a fun data set. Let me just put it up here. If I move it, you might be able to see where the real dots are. This is actually a classic paradigm in psychology, in visual perception. You have random dots, and then you have other dots that move coherently, and the monkey or human has to press a button to tell you which direction these things are moving. That's a previous life I had. Okay, so what is this data? So this data is actually, it's from the, I'm going to make it a little bit bigger. Maybe you can see it better. From the 1600s to 2000, it's sunspot activity, okay? And there's some interesting things in this data, which I didn't know about because I don't know anything about sunspots. But there is this thing that looks like measurement error or something like that. But that's not actually measurement error. That's something called the Maunder minimum. And that was a period in the 1600s where sunspot activity was very, very low and fairly constant. So that's interesting. And then there's something else in the data that you can't really see easily here, but you can see it sort of here. There is some periodicity in sunspot data. Many of you maybe know that. So what does the actual report say? So this is the executive summary in the report. It says, blah, blah, blah. Computer-generated text is never really fun to read. But what is it? the structure search algorithm has identified 8 additive components in the data. The first 4 additive components explain 92.3% of the variation in the data, blah, 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 blah. The first blah, 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 and so on. Short summaries of the additive components are as follows. Okay, first component it finds is a constant. Okay, and why is that? Well, actually, you know, that might not pop out, but if you look at this data, if you look at the axis, like these numbers aren't centered around 0. They're all starting from like, you know, 1,300 and something. So the most salient thing that's stuck out to the computer was that this constant is quite different from where it expected it to be. It's 1,300 and something. Okay, so what's the second component? The second component is a constant. This function applies from 1643 until 1716. Okay, so what is that? Well, that is the Maunder minimum. So the second thing that was most salient to the algorithm was this change point that happened somewhere between here and here. Okay, so it's 2 change points to sort of delineate the 2 ends of this minimum. What was the third most interesting thing for the computer? The third most interesting thing was a smooth function that applies outside until 1643 and from 1716 onwards. So smooth variation outside of that Maunder minimum. The fourth most interesting component was an approximately periodic function with a period of 10.8 years. This function applies outside of the Maunder minimum. So the fourth thing it found was the approximately 11-year periodicity of sunspot activity. Okay, and then these 5th through 8th components are sort of there, but you know, harder to see by eye. So this is what one of those reports looks like. This is largely the work of James Lloyd when he was in my group and co-authors. And then the report goes on, you know, with tables that are produced of R squared, and explanations of each of these components and what the residuals look like. And then, you know, showing what the extrapolations look like for the different components. And then a section I really like, which is called model checking, which basically goes and tries to falsify the assumptions of the model. It basically applies some classical statistical tests to see where the assumptions of the model don't match the actual data. This is a nice interface between classical and Bayesian statistics. And basically what it produces is a whole bunch of test statistics, and it finds something in bold, something that is significant. Okay? And then it goes and tries to explain that. So basically, the thing that it found is moderately statistically significant discrepancies in component 8. Okay. So that's nice. I like it when, you know, my algorithm can be self-critical. Okay. So that's it. That's an example of, let me see. The example of a report from the Automatic Statistician for Time series. This is now a few years old. We're actually revamping all of the code to be able to make another release. It's been a few years. We've had a change of like people, you know, PhD students and postdocs coming and going, but the project still lives on. So we're still doing things with it, and we're going to have another release fairly soon. One of the nice things about being systematic when you search over a big model space is that sometimes you actually get better predictive performance as well. So it's not just about being explainable and producing reports, but you know, the standardized root mean squared error in terms of prediction, where standardized is you know, 1.0 RMSE would be the best method. For the 2 versions of the Automatic Statistician, they're both better than the other things we compare to. This is over 13 data sets, box plot over 13 data sets. And in particular, if you compare them to just doing a linear model or just doing a vanilla out of the box kind of Gaussian process, they're about 3 times better than doing that. So doing a systematic search over kernels can help quite a lot. Model checking, I already mentioned. I think this is a hugely important area. If we're going to do automated statistics or automated data science, then we should also bake in all sorts of critical self-doubt into our systems so that they don't come out and overconfidently tell us things that are silly and wrong. Okay. So we thought quite a lot about model criticism. There was a paper that we wrote about this a few years ago. Now, the time series thing is the thing that we initially published for Automatic Statistician, but we've been doing a whole bunch of other things. One of the biggest applications of machine learning is classification, right? So almost, I would say, a large fraction of well-known machine learning applications are classification problems. So we also built an automatic statistician for classification, and it's different from time series model, but we're still using things like Gaussian processes. So here is a report that was produced by the automatic statistician for classification, like a 6-page report. And here are some snippets of text. It's using Gaussian processes, but it's now taking not one-dimensional time series, but it's taking multiple input dimensions and trying to predict some output class label. Okay? And so the nature of the reports that you would write to explain that are different than what you would do for just plain time series, 1D time series modeling. And one of the things that we focused on in these reports is concepts like, these are computer-generated text and tables from one of these reports. Concepts like interactions, additive interactions, two-way interactions. We also looked at things like monotonicity, like whether the class label was monotonically, the class probability is monotonically increasing or decreasing with a particular input variable. We use words like no evidence or little evidence or moderate evidence because we want the reports to be kind of readable, right? So if you pack them full of numbers, they're not easy to read. But if you say there is, moderate evidence that y increases monotonically with x, that's something that some people might find useful when they're analyzing their data. And just more examples of this. We've looked at other problems like transforming features. Let me show you, maybe I'll show you a couple of videos of the automatic statistician in action. Okay. Let's see if this works. It's playing, but it's playing somewhere else. Oh, it's playing down here, cleverly. All right, let's start again. Okay, so here is the sort of version, current version of the automatic statistician. It's not available for everybody yet, but we will put it online very soon. Sorry, you can't really see it because of the resolution here, but what do? You pick a file, you upload the file, then you click regression. We might even change the words to be something simpler than that. And it goes and it produces a report, basically. So it produces a report. The report actually, the video is just scrolling through the report. The report will refresh as the automatic statistician runs. So it's basically dynamically producing a report. It's evaluating models. It gives you instant gratification, or not nearly really instant, but gives you gratification as soon as it can. But then as it gets more data, and it runs more cycles, it updates that report for you over time. Okay? And that's one version of the statistician. Okay, oh yeah, here's the explanation demo. Okay, you upload the data set. The first bit is basically like it ingests the data and it tells you what it thinks the data is. How many rows, how many columns, whether they're outliers, whether they're missing data. And that's often a really, really useful sanity check, because one of the biggest failure points is you think you've given it some data, but actually your data is a mess and you didn't realize it. So it spits back to you any error messages that it gets from the data. Then it starts producing the report. Again, the report is dynamically being updated, basically. And in this case, the report is this is not very scalable yet. We can scale it. We have plans for scaling it. This is a report on a very classic data set called the IRIS data set. It's doing some clustering for you. It finds some number of clusters. It then explains what's in these clusters with some visualizations for you, etc. Okay. All right. So how I can wrap up fairly soon, I think. Yeah. So the last couple of things I wanted to say are a lot of this stuff takes compute, and it's sensible to be stingy with that compute. It's good to be rational about how you use your computation. And so the problem you're trying to solve there is that you want to trade off statistical and computational efficiency. And so we do this by treating the allocation of computational resources as a problem in sequential decision making under uncertainty. So a very simple case is if I'm exploring many, many possible models for a potentially large data set, then it makes sense to take a subset of that data, run it a little bit on a few promising models, and then allocate more computational resources to things that look more promising and less resources to the things that look less promising. And resources here means more data and more compute. So we automate all of that. And the end result is actually very, very nice. It's a very useful thing to be doing in the back end. And when you're trying to assess whether something is promising or not, you can't just look at its current performance. You have to actually extrapolate. You have to say, well, here, these are sort of learning curves as you put more compute into something. This learning curve looks promising because it's sort of shooting up. And I think if I give it just some more compute or more data, it's going to do way better than this other method that looks like it's already asymptotic. You have to make assumptions, and then you make decisions based on that. So we use an idea called freestyle Bayesian optimization, and we built that on top of that. And then we entered it into this AutoML competition, and it did very well there. So I think I'm going to just wrap up. So to conclude, the framework that I built all of this on is a probabilistic modeling framework. And it's a nice framework for automatically building systems that reason about uncertainty and learn from data. And I feel like we should be doing more and more automation just because it forces us to be more systematic. It forces us to be more rational and sort of cleans up our thinking often. And so that's the thing I've been mostly focusing on. All right. Thanks to lots of people who I've collaborated with over the years on this project. And there's a review paper I wrote about 3 years ago on probabilistic machine learning and AI, which you might be interested in. Okay, great.